Welcome to lab class. We're going to do our NMR skit shoot here, and actually we're not in lab for real, but this is what it would look like if we were at school. So instead of having an actual live skit to work out, we're going to do a virtual one. So here I'm your director. So hello class, it's too bad we couldn't all be in lab to do our NMR skit, but that's okay. We'll do the next best thing, film a virtual skit. Is the set ready, best boy Ahmad?
All set, boss.
Nice fanny pack, by the way.
Haha, thanks. You're rocking them khakis, by the way, Gramps.
Places, everyone, places. Quiet on the set. We are live in 3, 2, 1, action. So here's the original nerds came up with the first NMR. They used what's called a continuous wave NMR. So we'll start with the old wave first. Imagine the energy is going up on the screen. Here's our molecule. We'll start with the simple one. Let's how many groups of hydrogens does this molecule have? This is a methyl acetate. It has a 3 hydrogen signal here. Does it have any neighbors? Nope, 0 neighbors. There's another 3 hydrogen signal over here, 0 neighbors. They're too far apart to be considered neighbors. So that's a 3 hydrogen singlet. And it shows up at about 2 parts per million on the NMR spectrum. So about 2 parts per million downfield of TMS, the standard. And then this one's a 3 hydrogen singlet, shows up about 4 parts per million, a little less than 4 parts per million, but approximately. And page here is going to represent the hydrogens in their alpha and beta spin states. And so will Brenda. She'll represent another group. So first, though, we're going to need a magnetic field because you see how Paige and Brenda's alpha and beta spin states are at the same energy. That's because there's not a magnetic field applied. So first, we need to cue the magnet, Julia. Boom. There, she's got that strong magnetic field. And there it is. I'm going to represent her NMR magnetic field with that big purple arrow. And then cue the different spin state energies, Paige and Brenda. There's Brenda. See how now her alpha and beta spin states are not the same energy. And same with, that was Paige at first, then Brenda. And the alpha spin states are lower in energy and the beta are higher. Both, right? And I put a little symbol of a rotating like planet, like a spin. You could think of it that way. And these pictures are kind of small, but this is there's a magnetic field pointing upward on the alpha spin state, which is in a line with the NMR's magnetic field, lower in energy. And then the beta magnetic field, it's pointing down. It's opposing the magnetic field of the NMR, and that makes it higher in energy. And the difference in energy between Brenda's alpha and beta energy states, spin states, and the difference in Paige's spin state energy difference, they're not the same. So I put these two here to represent that. So you can see Paige's hydrogens are closer in energy and Brenda's are further in energy. Paige is holding actually the hydrogens that represent this 3 hydrogen singlet at 2 parts per million. And I got Brenda over here at 4 parts per million. And that's why, so 4 parts per million is higher energy than 2 parts per million. And there you can see it.
Welcome in Jacob, the radio frequency generator. And we need a radio frequency generator because the alpha and beta spin states of the hydrogens are at an energy gap that's in the radio frequency range.
And we have our first radio wave, Erfan. And Erfan, I wrote his name in jazz font here. It's kind of hard to read, but it's Erfan. So he's got a low energy radio wave, so I use Satchmo to represent that. And so his alpha and beta spins, he's going to affect an alpha beta spin state it's got a small energy gap. So,
and I think to myself, what a wonderful world.
Yeah, there it is. So Erfan's low energy radio wave corresponded to Paige's energy gap. So her alpha proton absorbed Erfan's radio wave, And what happens then is that alpha spin state page is excited, and now she has 2 beta spin states. There's millions and millions and more than that, but you can just think of 2 initially. So Erfan was absorbed, and he promoted an alpha spin state hydrogen to beta spin state hydrogen. And then our detector Damanpreet, she's over here. She's listening for these radio waves. Where's Erfan? He must have been absorbed, and he was by Page. Next up, we have a medium energy radio wave. This is Nikki, represented by the Beatles. And so let's see how Nikki goes. Ooh, it looks like Nikki did not correspond to the energy gap of Page or of Brenda, so she wasn't absorbed by the molecule. She passed through to the detector. And did you notice how I had the her wavelength was, well, her frequency was a little faster than the first one. Her wavelength's probably about the same, but I spent forever on this. It's like I went down the rabbit hole. Okay, so let's see what that means. So, hi Nikki, looks like you were not absorbed. So Damanpreet now knows Erfan was absorbed because she didn't see him, and she knows Nikki was not absorbed because she saw her. Next up, we have Douglas and his high energy radio wave. And I got Ronnie James Dio to represent that, the classic heavy metal band. Okay, so, yeah, he's higher energy, huh? Oh, yeah, looks like he was the right energy to excite Brenda. So Brenda's alpha spin state is going to be excited to the beta. And where's Douglas? He must have been absorbed. Yep, so Damanpreet had Douglas be absorbed. So this is a continuous wave NMR that we just did. That's where we send, you can think of sending each wavelength through one at a time and seeing whether it's absorbed or not absorbed. So the detector, Damanpreet, she knows that, so Erfan, a low energy radio wave was absorbed.
And I think to myself,
Erfan written in jazz. He was absorbed, oh, look at him shake.
what a wonderful world.
He caused this signal right here. He was absorbed by these hydrogens, which caused the signal at 2 parts per million. And then Nikki, a medium energy radio wave, was not absorbed. Remember, she passed by the molecule. And you can see I make her bounce a little bit faster. She's got a higher frequency than Erfan. Not absorbed. Douglas, a high energy radio wave was absorbed. You see Douglas written in heavy metal. Whoa, yep, see, he was high energy. His frequency was high too. So he's absorbed, and he was absorbed by the hydrogens over here on the carbon that's attached to the oxygen. And it's a 3-hydrogen singlet, and it's a higher energy, higher parts per million. The chemical shift 4 parts per million. That was fun. I want to see him shake again. Shake it low energy, low frequency, long wavelength Erfan.
And I think to myself, what a wonderful world.
Now you, a little higher energy, a little higher frequency, a little shorter wavelength Nikki. See how I made her shake a little bit faster? Shake your moneymaker, highest energy, highest frequency, shortest wavelength Douglas. I hope you're okay with me telling you to shake your moneymaker, Douglas. Woo! I like that one the best. I'm gonna do that one again. So now the detector, Damanpreet, says, I know which wavelengths were absorbed and which were not. I can make a spectrum with this data. And here it is. Now I'll label it. Remember, we always want to label our proton NMRs left to right, A, B, C, whatever, but actually this is our internal standard TMS. Here's our molecule, and we know that the 3 hydrogens over here are the singlet at 4 parts per million, because I told you already, actually, you don't know why yet, but I told you that's the case. And then B here. You might be wondering, why is A a shorter signal than B when they're both 3 hydrogens? Well, A must be a little bit wider because they're the same area, it's not just height. So A must be a little wider than B, but you can't really tell because we're too far back. If we zoomed in, maybe you could tell that this one's supposed to be wider. And cut. That's a wrap. Great job. Let's give our actors a round of applause.
And
Jacob,
I think to
Irfan,
myself, what a wonderful world.
Nikki, the medium wavelength, medium frequency, and Douglas, the high energy, high frequency radio wave. And the Manpreet, our detector, Paige, our alpha and beta spin state, and Julia, our magnet, and Brenda, our other alpha and beta spin state. Good job. Okay, you could take a break in your trailers. Next, we'll shoot a pulse NMR skit. All right, now we'll do the NMR skit shoot for the FT NMR, and we'll explain what that is. The FT NMR is the modern Fourier transform NMR. Do you remember that one, boom operator Ahmad?
That's the one where the NMR pulses all the radio waves at once, right?
Yes, pulsing all the radio waves at once and doing the Fourier transform of the collected data.
It can increase the NMR sensitivity up to 100 folds.
Boom! Someone ate their smart vitamins today. Places, everyone. Places. Quiet on the set. We are live in 3, 2, 1. Action! Fourier transform pulse NMR. Richard came up with this. He's the one who got the Nobel Prize for making this instrument so much more powerful. So our energy again going up along the side there. Here's our molecule, methyl acetate, same one again. We got the 2 3 hydrogen signals, a 3 hydrogen singlet about 2 parts per million, 3 hydrogen singlet about 4 parts per million. And we're going to use, Paige is going to be our representative again for the 3 hydrogen singlet at 2 parts per million. Brenda is going to be the representative of the 3 hydrogen singlet at 4 parts per million. But we do have a new cast other than that. We have Holden over here as the magnet. So cue the magnet, Holden. So before Holden turns on the magnet, the alpha and beta spin states are the same energy, but once the magnet's on, boom, then they cue the different spin state energies, Paige and Brenda. So Paige will now have her alpha and beta states, alpha and beta spin states separated in energy, and so will Brenda. And they're not the same energy difference. Brenda's got a bigger energy gap, and Paige her alpha and beta spin states are closer in energy. And our radio frequency generator this time is Demery. There it is, her and her pink flamingo. And our first radio wave, the low energy radio wave, is Stephanie. She's got Satchmo again. There's Stephanie. So the lowest energy radio wave, when that's sent through from Demery. Oh, actually, we're gonna pulse them all at once. I forgot. So let's introduce everybody. So here's the medium wave, medium energy radio wave. This is Tim. Tim has the Beatles there, and the high energy this time will be Ishmael. He's got a high energy radio wave, the heavy metal. So we need a detector Aliyah on the set. I'm sorry, Alina. Here's Alina, our detector, and you'll notice something a little different about it. She's not like just a regular detector. She also has a Fourier transform as part of her detection and creating a spectrum. We'll talk more about that. Detector Alina, you're turned off at the start. It's a little bit complicated, but you guys will get it. So in the beginning of the experiment, we're going to have detector Alina turned off. So cue blindfold for detector Alina. Boom. See how she's got a blindfold. So right now, she can't detect any radio waves. It should be actually, oh, I did blindfolds. Should have been earplugs because radio waves. Oh well. Cue radio wave pulse. Radio frequency generator Demery.
And I
Boom, here it goes. All of them are pulsed at the same time. Pretty cool, huh? You can see who's absorbed and who's not. And then both Paige and Brenda are excited. A lot was happening in that pulse of radio waves. Let's do another pulse, see it again. Okay, so watch carefully.
And I think to myself,
There we go. And they both get excited. And do you notice that the one radio wave that was not absorbed, Alina didn't detect it? Okay, let's do another pulse, and this time focus on the low energy radio wave, Stephanie. Okay, so we're going to focus on Stephanie. Notice how she's absorbed by Paige. So, okay, here we are. We got our...
and I think to myself,
She gets absorbed by Paige, yep. Good. And now, here's another pulse. Now we'll focus on the medium energy radio wave, Tim. So here's a go. Here's Tim. That's what we're going to focus on. Notice how he's not absorbed or detected. Detector Alina has her blindfold on. She's off. She can't even see him. So here we go. So here's Tim. He's got like a medium frequency there. And look at that. Passed right by Alina. She had no clue. And finally, we'll do one more pulse. Focus on the high energy radio wave, Ishmael. Let's see where he goes. He's the fast one. Here he is. Notice how he's absorbed by Brenda's hydrogens.
and I think to myself,
He's going crazy. He's going crazy. Boop, and he stopped right there. Yep. And he excited Brenda. Wait a minute. The Alina detector is off. How is data collected? Great question. He's getting it. Yes, Holden. I always knew you were a smart kid. Dina didn't raise no fool. That's my boy. So this is Holden's mom. She's a friend of mine. I knew Holden when he was a little kid. Well, the Alina detector is off until all the non-absorbed radio waves pass by. So she's turned off, and the ones that are not absorbed, the radio waves that are not absorbed, pass right by. Oh, that's my boy. Should have gone away already. That's okay. Then after all the non-absorbed radio waves pass by the Alina detector, she's turned on. Cue blindfold removal of Alina detector. Boom. See that? It went kind of fast. So Alina's got her blindfold on. Now it's off. Okay, so now she can detect radio waves. Detector on. Next, the radio waves that were absorbed get released as the hydrogens relax back to their lower energy alpha spin states. So right now, the Paige's all of her hydrogens in the beta spin state. They want to relax back down. Some of them will relax back down to their alpha spin state, and when they do, they'll release the radio wave, a wavelength of radio wave energy that was the same as was absorbed. Same thing for Brenda. So the radio waves that are released are detected by Alina detector. That is now on. Detector is on. So here we go.
and I think to
They
myself,
relaxed, and then they're detected. Stephanie and Ishmael are detected. So let me go back and see that again. See how they're both excited, and then they released their radio waves, and now that some of them came back down to the opposite state. Hello, low energy Stephanie. Hello, high energy Ishmael. I detect you. Isn't that cool? In FTNMR, the Alina detector detects the wavelengths that were absorbed, then released. It's the opposite of the continuous wave NMR we saw earlier. In that one, the Monpreet detector detected the non-absorbed radio waves. Okay, let's do one more take for coverage. Cue Alina detector to be off, blindfold. Whoop. Now she's off. Pulse all the radio waves. Tim, who's not absorbed, just passes by the detector. Cue blindfold removal. Now the detector is on. And cue relaxation. Paige and Brenda relax and release their radio waves, which are then detected by Alina. Hello, low energy Stephanie. Hello, high energy Ishmael. I detect you again. Detector Alina got all the released radio waves at about the same time. We say the data was in the time domain. And here's a graphical representation of that, the time domain. So she got all those radio waves at the same time. Some were higher frequency, some were lower frequency, some were medium, and they're all just a mess on top of each other. We call this data the free induction decay, or FID, because those high energy beta spin states of the hydrogens, they freely decayed to lower energy alpha spin states. So that's the FID. That you can't really look at and understand what molecule you have. That's not really a spectrum you can look at and go, oh yeah, it looks like I got this and that in the molecule. We need the data in the frequency domain over here. So remember, chemical shift values, the parts per millions, are calculated from Hertz values, and Hertz is a frequency value. So that's the frequency domain, our spectrum. The mathematical operation that takes the time domain data and transforms it into the frequency domain is called the Fourier transform. And you don't have to worry, we don't actually do it, and that's where the FT comes from. The computer does it for us, we just tell it to do it. And you can see how I like this representation of it. Like, this lower frequency one can be separated out in here, and here's the higher frequency one separated from the lower frequency. You can read the spectrum. FT NMR, don't worry, our computer does the math. We can take multiple pulses of the radio waves and average their data to get great spectra. So you don't have to just do a single scan, you can do multiple scans and average it out, and then that's where you get your sensitivity. And also these pulses only take a short amount of time, where the continuous wave, it takes much longer to scan through each wavelength. So this was a big advance in science when it was discovered. So FT, or pulse NMR, modern and better. Summary. So Stephanie, a low energy radio wave was absorbed. Stephanie written in jazz. She's that signal, the 3 hydrogen singlet at 2 parts per million. Tim, a medium energy radio wave, was not absorbed. Ishmael, a high energy radio wave, was absorbed. He's the 3 hydrogen singlet at about 4 parts per million. I know which wavelengths were absorbed and which were not. I can make a spectrum with this data. Now I'll label it A, B, TMS. Here's our molecule. That's A and that's B. Now, would you be able to tell me this is A and that's B? Not yet, but shortly we're getting to it. You'll be able to. And cut. That's a wrap. Great job. Let's give our actors a round of applause. Demarie, this radio frequency generator, and her pink flamingo. And Stephanie, our low energy radio wave with Satchmo.
What a wonderful world.
Tim, our medium energy radio wave, the Beatles. And Ishmael, our high energy radio wave, the Dio there. Dio's the best. He's this little guy with this huge voice. He just rocks. Well, he passed away, but his music's pretty fun. All right, Alina, our detector. Paige, again, doing a great job with the alpha and beta spin states, along with Brenda doing a great job. And Holden, our magnet. And Mama Dina. Good job. Now off to the press junkets. Okay, back in lab, virtual lab here. Wow, that was a lot of work, right? Great. Right, cameraman Ahmad?
But it was worth it. It came out so good.
You're right, Ahmad.
I'm always right, boss.
The end. I hope you liked it. That took forever.
And I think to myself, what a wonderful world.